Okay, so what does a Mobius strip have to do with trying to compute 0 divided by 0? So first off, what is a Mobius strip? So if you've not seen it before, you take a rectangle, a strip of paper, you make a half twist, a 180-degree twist in one side, and you attach the ends together like so. Right. And famously, this only has one edge, you can go all the way around, and it only has one face. Inside and outside are the same face. Okay, so that's the Möbius strip. So how about 0 divided by 0? Well, as any calculator will tell you, 0 divided by 0 is undefined. Right? If I've got no apples and I distribute them among no people, how many apples am I going to give each person? Well, there's not really a wrong answer, there's not really a right answer either. It's just undefined. And in fact, there's a nice geometric way of seeing this exactly the same ambiguity as well. We'll start with an ordinary looking xy plane, nothing special. Now, fixing a point x, y, let's say 1, 2, remember that the value y over x is nothing but the gradient of the line joining 0, 0 and xy. So in this case, 2 divided by 1 equals 2. Okay, now where does 0 divided by 0 fit in? Well, if you like, that's just asking what's the gradient of the line that passes through the origin and the origin. And again, there's not really a wrong answer or a right answer. It's just undefined. And so to explore this a bit further, we're going to think now about the function defined by setting f of x, y equals y divided by x. This is a function of two variables, x and the y. And all it does is take a point xy, computes the gradient of the line passing through the origin and the point xy. So if you like, you could think about plotting a 3D graph, if you like, with f of xy as the height. Think about the height of a landscape. So x and y, your coordinates of your position in the landscape, and then z could be your height, your f of xy. Okay, and we'll point out that places where f of xy is constant, like say or equal to 2, that's nothing other than straight lines through the origin here with gradient 2. So just a straight line through the origin, gradient 2. So we can think about those straight lines through the origin as the contours of this graph. So for the fun of it, here is the graph of the function f of x, y equals y over x in 3D. And you can see that if I fix a line y equal mx for some gradient m, that line is a contour for this graph. Actually, one more thing about this graph. If we plot each of the lines y equal mx from very large values and very high gradients down to very low gradients, you can see that I'm making a 180-degree rotation, or a half twist of my lines as they go down. And that might start to be suggestive. Okay, now I really need to address a couple of the ways that the surface that we have here is not really a graph, places where this function, if you like, breaks down. The first of those is that we miss out the y-axis. If we look along the line x equals 0, we don't have points in our graph lying over that. So we can fix this by, if you like, gluing in the vertical line. Okay, so what do I mean by that? Well, if we look at very large z values, our contour looks like a line which is very nearly vertical. I mean, if we look at very, very negative values, like large negative values, and again, we see our line becomes nearly vertical. So what we want to do is to take that z-axis, if you like, and wrap it up into a circle, and those contours, those nearly vertical contours, should be glued together using a vertical line. And that's made a shape which is now should be familiar or maybe expected. You know, it's made us a Mobius band again. Okay, so I'm brushing a few technical details under the rug, but one way we could head towards making this gluing a bit more precise is by replacing the idea of that gradient function y over x with the function taking each point at x, y to the angle made between the positive x-axis and the line through 0, 0 and xy. The range of this function now is actually a circle, and there's no problem there with vertical lines, right? You had to have an angle of 90 degrees. There are actually a couple of good reasons not to do this. The first of which is technical and is to do with the fact that the function y over x is algebraic, so this construction is, if you like, a completely algebraic one and can be made completely algebraic, even with the gluing. The second one is we need to be very careful about exactly which circle we're mapping into using this angle function, because it's not necessarily the one you first think of, here at 360, because as we turn 180 degrees, we in fact hit the same line again, and that's a fundamental point here. Another maybe slightly cryptic comment is that this f of x, y is y over x, you can think of as the projection of the plane from the origin onto its circle at infinity. So that might not be meaningful, but at least it sounds neat. Right, so the other place this 3D graph has a bit of a problem is along the z-axis, where it clearly isn't one-to-one. It's probably multi-valued. Looking at that contour map, all the contour lines cross there. And that's exactly this problem that we're trying to compute 0 divided by 0, which can't be uniquely defined. Okay, so to fix this problem, that f of x, y is just not defined at 0, 0, we could replace our entire plane with this Mobius strip. We now gain this entire z-axis. And now we can replace the function f of x, y with the height function z. Okay? So everywhere away from the z-axis, that does exactly the same thing. It takes our point x, y to the height of that graph, which is just the gradient, remember, of that straight line through that point in the origin. But we've gained this entire sort of central band, right? So now our function is defined at every point on the z-axis because we've, if you like, separated the origin out into an entire line of points. So now we can make sense of that function, y over x. And that's a really standard technique in algebraic geometry called, somewhat dramatically, blowing up. And it's most commonly used in this way as well, for extending functions which aren't quite defined everywhere, or if you like, more generally, taking points where collections or families of curves intersect and separating them out. So there we have it. What did the Mobius strip have to do with finding 0 divided by 0? Well, if you want to define 0 divided by 0, you've got to modify the plane by turning it into a Mobius strip. Okay, there we are. Thank you very much for listening. I hope you enjoyed.